In this video, we will talk about inverse functions. So inverse functions will come up again later on when we talk about logs and exponentials, but I kind of wanted to give you a little bit of the gist of what inverse functions are and what I'm going to be looking for when we talk about inverse functions. So let's just briefly just talk about it for a bit. So first thing that you want to know is what exactly is a one-to-one function. So a one-to-one function basically is that for every y, well, we know that f of x equals to y. That's what we kind of know, right? And what we want to know in this case is that there's only one x for every y. That's what a one-to-one function means. So if I were to kind of look at the graph, like let's say we look at the cubic one, we can see that there is only one x for every y. So if I choose this y coordinate only corresponds with one x. Okay, so for one x, you only have one y, but every y, there's only one x. Okay, so it's vice versa. Whereas this guy, if I were to have a parabola, you can see that for this y value shares two different x's. Huh, that's funny. Okay, so it has two different x's. Okay, so this guy is not one-to-one because this y value has two x's. Okay, this x1 and then this x2. So a way that you can know whether something is one-to-one is called the horizontal line test. So you can check this by doing a horizontal line test. Okay, and basically what the horizontal line test says is that horizontal line can go through the graph only once. Okay, so the parabola itself is not one-to-one because it crosses the graph twice. Now it's a function, it's just not one-to-one. Now, one of the good things about one-to-one functions is that there's inverses that exist. So an inverse exists if something is one-to-one. So an inverse, okay, is just a function for which the input of the original function becomes the output of the inverse function and output becomes the input. Okay, so that's what an inverse function is. It's just a function for which the input of the original function becomes the output of the inverse function and the output becomes the input. Okay, and the way that we kind of write inverse functions is this notation f inverse of x. Okay, this should not be confused with a power of -1. So this is not equal to this. Okay, so this is just fancy notation with the -1. Okay. Now, one of the things to kind of know about inverse functions is that a function has an inverse if the function is one-to-one. So if I know this function is one-to-one, then it is going to have an inverse. Okay, so we know that the inverse is going to exist. Now, one of the things that is really cool about inverses is that, and this is why we really care about inverses, is that we know that a function has a domain and range. Okay, So that means that the inverse function should also have a domain and range. However, because the input and the outputs are now swapped, the domain of f of x is now going to be the range of the other one. And the range of f of x is going to be the domain of the inverse. That's what's really cool, because before we couldn't even find the range of anything, okay? And in order for us to find the range, we would have to graph the function, which can be a little tedious. But now, if we can figure out what the inverse of something is, then we can try to figure out the range of the original function. So graphically, if we were to look at the function itself, let's say this is the original function, f of x. What this kind of looks like, because we're changing up all the x and the y values, imagine that you have a straight line y equals x here. So this is the graph y equals x. So the inverse function is basically going to be a mirror image of this thing. So it kind of looks like that. So this guy is the inverse function. So you changed all the x's and the y's. Okay, so that's the inverse function. So these are just reflections of each other. So it's reflection about y equals x. Okay, all right. So how do you know if you have two inverses? Okay, so how do I know if two functions are inverses? Well, the way that you can do, because we know that there's a reflection about y equals x, well, you need to check this. So you got to check that f of g of x equals x. So when we plug in the function, whether you want to plug in the other one or the inverse, they need to equal x. Okay, so basically you are undoing it, and all you're left with is with x. So let me give you an example. So let's say we had f of x is equal to x cubed minus 4. And let's say you had g of x is equal to the cubed root of x plus 4. Are these guys inverses or not? So one way that we can check either one. We can either check this guy or we can either check the other one. It doesn't matter. So I'm going to check this guy, f of g of x. And I need to make sure that this equals x. So what I'm going to do is that I'm going to plug in g of x. So g of x in this case is this cubed root of x plus 4. Okay, so I have this guy. So I'm going to start off by plugging this entire thing into f. So let's write down f. So that's the x cubed minus 4. That's this guy. So what I'm going to plug into the x is this cubed root thing. So I'm going to plug in the cubed root of x plus 4. And you can see that the cubed and the cubed root are going to go away. So I'm left with x plus 4 by itself and then a minus 4 on the outside. This is going to cancel out and you're left with an x. Okay, so what can you tell me? F of x and g of x are inverses. Okay, so that checks. Okay, now the million-dollar question though is, how do I find an inverse? So if I know that an inverse exists, how do I find it? Okay, so the way that you find an inverse is the following way. The first thing that you gotta check is that f must be 1 to 1. That's the first thing that you gotta check. If it's not 1 to 1, we are done. We do know that this is not a there's no inverse that exists. The second thing is change x to y and y to x. So you gotta change those guys. And then the last thing is solve for y. Okay. All right. So this is basically the directions that you gotta be able to do. I will give you one more direction. Change y to f inverse of x. Okay, that's usually just to remember that that is actually the inverse. So let's do a couple of examples. So let's say we want to find the inverse. Okay, so we have f of x is equal to 3x minus 4. So the first thing that we can see is that this clearly is 1 to 1 because this is just an equation of a line. Now let's change the y to f of x. Okay, so I changed y, f of x to y. Now what I'm going to do is I'm going to change the x to a y and the y to an x. Like so. And now what I'm going to do is I'm going to solve for y. So I'm going to add the 4 over. So I have x plus 4 equals 3y. I'm going to divide the 3 over. So what I'm left with is y is equal to x plus 4 over 3. And now the last thing that I got to do is change the y to f inverse. Okay, and that's the answer. Okay. Okay, so let's try another one. So let's say we have something that looks like that. So the first thing that you do is let's change this to a y. And now let's interchange them. So now y is going to be your x. And then the x is going to be your y. And now let's solve for y. So we want to solve for y, so let's move the 2 over. Okay, so you have x minus 2 is equal to the square root of y minus 3. So now let's square both sides to get rid of that square root. So you got x minus 2 squared equals y minus 3. And now finally I'm going to add 3 to both sides. You got that y is equal to x plus 2 squared plus 3. Okay. All right, so now finally we're just going to change the y to f inverse. Okay, so that's my answer. Okay, so let's do another one. Okay, so we want to find the inverse of f of x equals x squared plus 1, and then x has to be greater than or equal to 0. Now, why would you want this x is greater than or equal to 0? Well, let's think about what x squared plus 1 looks like. X squared plus 1 is a shifted up 1 unit, and it looks like that. This guy is not 1 to 1. However, if you get rid of this part, now it's 1 to 1. If I only consider from 0 all the way to the positive side. It's kind of how we did with in trig with inverse trig functions where you restrict the domain. So here you're restricting it. So now you can have an inverse function. Okay, so now let's do that. Under this restriction, we're going to change y is equal to x squared plus 1. We're going to subtract 1. We're going to change the y to an x and then this to a y. Let's subtract 1 over. So you have y squared is equal to x minus 1. And then finally, we're going to take the square root. Now, when we apply a square root, we always write plus or minus. So we have y is equal to plus or minus square root of x minus 1. But we have this restriction. What can you tell me about the x's? The x's are always positive. So we're going to choose the positive side. Y equals the square root of x minus 1. And then finally, we just change this to f inverse. Okay. Now let's do one last problem that's a little bit more involved. So let's say you had f of x is equal to 3x plus 1 divided by 2x minus 1. So let's change up the y, the f of x first to a y. And then let's change this to the same thing. And now let's interchange them. So now this is going to be your x and the other one's going to be your y. Okay. So now let's solve for the y. So here you have to be very particular. So you have x and then 2y minus 1 is equal to 3y plus 1. So basically what I did is that I multiplied both sides by 2y minus 1. Put parentheses around it. So now this cancels out with that and you have that left over. So let me distribute this guy out. So I get 2xy minus x equals 3y plus 1. Okay, so now let me move all the y's together. So let me move this 3y over. So I can put all of my y's together. So I have 2xy minus 3y minus x is equal to 1. And now let me move that x over because I don't need it. This x doesn't have a y. So I have 2xy minus 3y equals x plus 1. So here what we can do is that we can't quite isolate the y, but we can factor out a y. I'm going to factor out a y, snatch a y from there, and what you have is a 2x minus 3 equals x plus 1. And now what we can do is we can divide both sides by 2x minus 3. So this goes away, and you're left with y is equal to x plus 1 over 2x minus 3. And the last thing to do is just write f inverse. Okay, and that will be the inverse of that. Now, one thing that you can kind of do, or when you do these types of problems, is that you can kind of think about the domain and the range. So remember, our original function for this problem was 3x plus 1. Okay, so our original function was 3x plus 1 over 2x minus 1. So that was the function. The inverse of that was x plus 1 over 2x minus 3. If I wanted to know what the domain and range was of the original function, well, the domain for this guy is just setting the denominator equal to 0. So that means x cannot be equal to positive 1/2. Okay, so basically the domain is from negative infinity to 1/2. Union 1/2 to infinity. So that's the domain of this guy. Now, what about if I wanted to know the range? Well, if I wanted to know the range, I would have to graph this. But now that I have the inverse, I don't have to graph it because I can just find the domain of this guy. Because the domain of the inverse is going to give me the range. So the domain of this guy is just taking this equal to 0. So x in this case cannot be equal to 3/2, which means that the domain is just a range over here for negative 1/2 to 3/2, union 3/2 to infinity. So it's really, really easy to do. We don't have to graph it. We just need to solve for the inverse, which actually might be a little bit easier to do than just graph this crazy function. And actually later on, we will graph these types of rational functions. But this is a really quick and easy way, well, kind of easy way to find the range of this particular function.